let's just talk about, in general what it means to be an inverse, okay? Now you don't have to write this down, but if you had a table and let's say you had the 0.35 and the 0.48 in it, the inverse would just be switching the x and the y's, okay? So then you'd say 5 would give me 3 and 8 would give me 4. That's all an inverse is. It's switching the inputs and the outputs. Now, the definition of an inverse, it looks really complicated, and I will definitely explain it to you. Just be patient on this definition. It says, and this is the inverse notation. So this is the inverse of f of x is the inverse of fx. If you read it, it kind of sounds funny, but they're just showing you the notation. If, and then you write the inverse notation, and then you plug the function into it, and you say that would have to equal x. And of course, I'll be happy to explain that to you, but let's write it out first. Then I want you to do the same thing, but this time put the inverse in the inside, and then write equals x. Okay. Now, for right now, I just want you to write it down. And then, like I said, I promise I'll explain it to you. Okay, so then I said the domain of the function must be equal to the range. And so this domain should be equal to that range. And then I said the range of the inverse must be equal to the domain of the function. So the domain and range is flip-flop. Okay? So you have this flip-flopping of the domain ranges, flip-flopping of the inputs and outputs. Okay. Then I said here, in other words, and this in other words I think will make a lot of sense. If a comma b is on f of x, then what point must be on the inverse? We're going to yell it out. If a, b is on the function, then what would be on the inverse? BA. The input and output switch. In other words, if I know in my function 3 gives me 5, then I want the inverse where I say, if I put in 5, I want to get out 3. So I want the inputs and outputs to switch. Sometimes when you have functions, you have the inputs and you're looking for the outputs. Sometimes you have the outputs, you're looking for the inputs. That's what the inverse does. Instead of saying, I know 3 gives me 5, and what input gives me 5, I could say, if the input's 5, then what gives me 3? I'm basically switching this point around. So if AB is on a function, then switching those around, BA is on the inverse. And then I'm going to write the same thing in function notation, okay? So this says if f of A equals B, and I'm going to do inverse notation, and I'm going to say if I plug B into the inverse, I should get out, what should this be? Just A. Okay? That's what it means to be an inverse. That if you take the inputs and outputs, you're just switching them. So again, if 3 gives me 5, now on the inverse, 5 would give me 3. Okay. Now I'm going to try to explain this notation to you a little bit, and take a look at this so you can make sure you understand this, right? You put an input into a function and you get an output. You put that output into the inverse, you get that original input back out. Now let's take a look at this right here. I'm going to zoom in and I'll zoom out in a second. Okay, let's just look at this right here and see if we can understand this. Some number goes into a function and an output comes out. Okay, so this is some output. Now you put that output into the inverse. And what you have to understand is here, then the output of the inverse should be that original input. That's what that means. Okay, in other words, let's use these numbers as an example. If I put 3 into this, this would equal 5. And if I put 5 into the inverse, I'm getting back out 3. I don't know, does that make a little bit of sense? All right. So, I mean, that notation is not super easy to understand, but you plug something in, you get its output. When you put that output into the inverse, you get that original output back out. So that's true for any x. So that's what that notation means. And honestly, you could do all these problems even if you don't understand that notation. But if you understand what an inverse is, it might take some time, but you can understand why that actually makes a lot of sense. And in some ways, it's almost obvious, but the function notation is kind of weird and takes some getting used to. So let's talk about finding inverses. To have an inverse, a function must be 1 to 1. Okay, now let's talk about what it means to be 1 to 1. Okay, let's go back to my example here. If I said, 3, you would say that goes with 5. If I said, what input gives me 5, you would say 3. But let's say I had the point 5, 8 here. This is not 1 to 1. Because if I said, 4 gives me 8, that's still a function, and 5 gives me 8, that's still a function. But if I said, what gives you 8, you would say 4 or 5. So that's not 1 to 1. Okay, let me give you a practical example of this. We talked about ID numbers and birthdays. That's a function, right? You say, what's your ID number? And then plug in ID number, you get out a birthday. Because no one has 2 birthdays. But if you do it the other way around, let's look up a birthday, see how many ID numbers. That's not 1 to 1, because I'll get more than one thing out. So something that would be 1 to 1 if I did like ID numbers and social security numbers. If I looked up your ID number, I would get your social security number. If I looked up your social security number, I would get your ID number. That's 1 to 1. There is no other way that could be. So to be 1 to 1, and write this down, a function is 1 to 1, writing 1 to 1 again. It passes the, you know what this is? Horizontal line test. That means every x matches up with a single y, and every y matches up with a single x. Or you can say every input matches up with a single output, and every output matches up with a single input. Or you could say every element of the domain matches up with one element of the range, and vice versa. So there's a lot of different ways to word that. So let's talk about an example of a function that is 1 to 1 and talk about its inverse. And I'll zoom back out in a second, but I'm going to write this on the side here, and we will talk about it. X cubed is a great example of a 1 to 1 function that has an easy inverse to understand. So if you don't want to draw this, you can just watch me do this. But I like this example, x cubed. Okay, so you might draw it in the corner. Now, it's not hard to understand why it's 1 to 1. Not all polynomials that have cubes are 1 to 1, but plain old x cubed is 1 to 1. It looks something like that. And let me explain what I mean. If I say any input, there's a single output, right? If I say plug in 2, you'd say 8. If I say plug in -2, you'd say -8. If I say plug in 1, you'd say 1. Okay? Now, same thing with outputs. If I say an output, there's only one input that goes with it. If I said the output's 8, you'd say the input's 2. If I say the output's -8, you'd say the input's -2. So every input has one output, every output has one input. It passes the horizontal line test and the vertical line test. Follow me so far? Okay. Now, you know the function that is the inverse of cubing. Yell it out. What's the inverse, the opposite? Cube root, okay? Cube root I like because it's also 1 to 1, and it has a domain range of all real numbers. Both of these, the domain range is all real numbers. Okay, now, cube root, when you draw a picture of this, try to have it curved up and then curved down like this. So like the name for that is concave up and then concave down. These are going to overlap at 3 points. My graph is okay, but they're going to overlap at 3 points. So I want to put 3 bold points here. Bump, bump, bump. Okay, I kind of overdid it with the size of those points. There's 3 points that they overlap at, and the green one is the inverse one, and the other one, they're inverses of each other. So they're inverses of each other, and they look like that. Okay, so let's talk about these 3 points. This point is 1, 1, right? 1 cubed is 1. This point is 0, 0, right? 0 cubed is 0. And this point is -1, -1. Do you see how those 3 points have the same x and the same y? So next thing I want you to do is I want you to draw a line that hits those 3 points. Does somebody want to raise their hand and tell me what the equation of that line is? That line that hits those 3 points. It's the line of reflection from the purple to the green. Go ahead, Doug.
Y equals x.
It's y equals x. Okay. So when you do an inverse, it's reflection over the line y equals x. And I'm going to tell you a really good way of remembering this. Okay. I think this makes a lot of sense. You can decide. Some people just memorize it. They just memorize, like, they just sit down and they say, when I do even functions, it's over the y-axis. When I do odd functions, it's over the origin. When I do inverses, and you could do that, okay? And you might need to study these kind of things. But let me tell you why this makes sense. The x's and the y's switch. So you don't have to put this point down if you don't want, but this point right here is 2, 8. And then on the inverse is 8, 2. So the x and the y switch, right? So the x becomes the y becomes the x. But there's some points like 1, 1, where if you switch x and y, it's the same point. You following me? So points like 1, 1, or 5, 5, or 6, 6, or 7, 7, those don't change. So points where the x and the y are equal don't change. So when the x and the y are equal, those points stay in the same spot, which is why it makes sense. It's reflection over the line y equals x. So it's reflection over the line y equals x, and you can remember it by saying the points where the x and y are equal stay the same. And so that's why those are like, important points to think about. But it's reflection of the line y equals x. Okay, so that's something about inverses. Now, the process for finding an inverse, my guess is you've seen, but there's more to it than maybe you've been told in the past. You can tell me as we go here. All right, what kind of function is this? Yell it out. It's a line. Yep, it's a line. Is this line 1 to 1? Does it pass the horizontal line test? Yeah. All lines that are not horizontal do pass the horizontal line test. Vertical lines are not even functions. So any line that is diagonal, has a slope that's not 0 or undefined, is automatically 1 to 1. It will have an inverse. Okay. So what I do is I make the f of x, y, and I switch the x and the y, and then I solve for y. Does this look familiar? Where you switch x and the y and you solve for y? Okay. For 1-to-1 functions, this is the way you do them, and 1-to-1 functions are easy. 1-to-1 functions, you switch x and the y, you solve for y, boom, you get the answer. Okay? So this one's 1-to-1. We're not going to spend a ton of time talking about it, but there are some things we have to talk about for when it's not 1-to-1. So anyways, this one's 1-to-1. Switch x and the y, that switches the inputs and the outputs. That's the whole point of inverses. And then I'm getting y alone. It's possible that you've learned these steps, but you didn't understand why you were doing them. It's possible that you never really thought about domains and ranges. I am going to make this look like a y equals mx plus b line. If you left it x plus 1 over 3, that wouldn't be wrong. So if you said x plus 1 all over 3, that would still be acceptable. So there's a lot of different versions of how you can write this. So if you're worried about how you can write this, don't worry about how you write it. Either way is fine. Okay, you follow me so far? Okay, this one's 1-to-1 also. We're not going to spend a lot of time talking about the domains and ranges of this one because it's not really interesting, the domains and ranges, because the domain and range of both of them are all real numbers. So the domain and range, all real numbers, and when you do the inverse, it's all real numbers, all real numbers. The domain and ranges need to flip-flop, and I'll talk about that as we go. And they do flip-flop. It's just that they're all real numbers. So this is the answer to this one. Lines are the easiest type because they're 1-to-1, and you get this answer. You solve for y and you get this answer. Okay. There's a problem with this next one. It says fx equals x squared. Find the inverse. What is the problem here? It's not 1-to-1. Okay, so we have a problem right from the beginning. It's not 1-to-1. So if you were asked the question, is this 1-to-1, you would just say no. Okay, if that was the only question, is this 1-to-1, you would say no. So technically, we cannot find an inverse of this function. Okay, but we could do something called restricting the domain. So if I was going to ask you this question, I wouldn't just say find the inverse. I would say something like, how would you restrict the domain to find the inverse? Or restrict the domain and find the inverse. What that means is we have to chop part of this graph off and change the function so we can find an inverse. So I want you to write this down. I want you to write domain. I want you to write restricted domain, which I'll explain what that is. And then range. You could abbreviate some of this if you want, but domain, restricted domain, range. The domain of this function is negative infinity to infinity. You can plug any number in x squared. The range is not all real numbers. The range, the lowest value you can get is what? 0 and then to infinity, correct? Okay. So when you have a function that's not 1-to-1, you can do an inverse, you can find an inverse, but you have to restrict the domain. You already know the opposite, the inverse of squaring. What's the inverse of squaring? Square root. Okay, it has an inverse. So it's not like there's no inverse, there is an inverse. But when mathematicians came up with square root, they needed to be aware that this is not 1-to-1, and you have to do some math that maybe you never thought about, but you have to restrict the domain. So you have to chop part of the graph off. Now, when you're chopping part of the graph off, you got to keep the range the same. So I can't just be like, oh, let's just chop off all of this up to right here because I like the number 5. You have to keep the range the same. So we're going to chop off all of this part of the graph. Okay? And what about this point 0, 0? Should I leave it or get rid of it? That you leave. So you chop off everything up to that point. And we're going to write the restricted domain. These are x values. So x's are going to be 0 to infinity. These are x's. The ranges are y's, just to remind people of that. So if you were asked on a test, how would you restrict the domain? You could chop off the left-hand side or the right-hand side, but you don't want to get rid of 0, 0. Okay, now we're going to do it the way, that is easier and the way that, mathematicians have done this particular problem. They didn't chop off the right side and leave the negatives. They chopped off the negatives, left the positives. So, but if you were asked, you would have the choice. Okay? All right. So, now we're going to do the old switch the x and the y thing. So I'm going to rewrite the function with y. I'm going to switch the x and the y. Okay? So you rewrite the function with y, switch the x and the y, then you get y alone. Now, do you notice I threw the square root of both sides? The square root of both sides thing is a complicated issue of math that takes a little bit of understanding, okay? You are supposed to put positive or negative, and you are considering whether positive or negative makes sense. Sometimes the positive makes sense, sometimes the negative makes sense, sometimes they both make sense depending on the problem. Every time you do the Pythagorean theorem, you never put the negative. You always do a square root in the Pythagorean theorem and you never put the negative because the negative never makes sense, okay? And on this one, we're not going to put the negative because the negative is not going to make sense. Because we don't want a non-function. We want our inverse to be a function. That's the whole reason we chopped off the left side of the graph. Okay? Now, let's write in function notation. And if this is still unclear to you, I'm not done explaining it. Okay? Okay. Now, let's go on our graph and graph a square root function that starts at 0, 0, and it goes like this. Okay? Now, does that look like a reflection over the line y equals x? Yeah. So it's not the parabola that was flipped over that line. It was the right half of the parabola flipped over the line. See, if I take a parabola and flip it over this line, I'll get a sideways parabola, which is not a function. Your inverse needs to be a function. That's the original problem. So the original is not one-to-one, so I can't just flip it over the y-axis because then it won't be a function. All right, so I chop the left side off. I got this square root is a function. The square root function, if you plug in a number, you don't get two numbers out, you get one number out. Square root of 25 is 5. Square root of 9 is 3. And so that one is a function. Now, I'm going to write the domain range of this. So for our inverse, this is for the inverse. I don't know if you want to write down like this is for the inverse. The domain is 0 to infinity, and the range is 0 to infinity. It's up to you if you want to draw these lines or not, but this is what you have to understand. This range has to become this domain. And our restricted domain has become this range. So the domains and ranges flip-flop. The domain becomes the range becomes the domain. And that happens, and it has to happen. Any question about this so far? Okay. So that's restricting the domain. If I gave you like an absolute value function, I said, how would you restrict the domain? You do the same kind of thing as this. You cut the left side of the graph off. Let me explain why this is going to be important in the future. And don't draw this. Think about a sine curve. Sine is like a wave, right? Okay. Does a sine wave pass the horizontal line test?
No.
No, it fails it miserably. A horizontal line hits it an infinite number of times. Okay? But there is an inverse sine function, and we're going to have to restrict the domain, and that's a future lesson, and you just have to worry about it now. But you have to understand this whole idea of restricting domains and ranges. So then we get to sines and cosines and tangents. They all fail the horizontal line test, and they all have inverses, and you have to restrict the domain to find those. Okay, let's do another problem. Different type of problem. This one is a square root function. Okay. We're going to draw a little sketch of it. We're going to write the domain and range. So this is a square root function. Is it shifted down or left or right or up, or which way is this shifted? What does this minus 2 do to it? Right 2. So it's a square root function shifted right 2. Is that one one-to-one? Yeah, that one's one-to-one. It passes the horizontal line test. You can't hit it twice with a horizontal line. It's one-to-one. So if I gave you an output, there's only one input that goes with it. If I gave you an input, there's only one output that goes with it. Let's do the domain and range here. So the domain starts at 2 and goes to infinity, the range, yell it out, what's the range? 0 to infinity. Okay, now, this is what you have to understand. When we do the inverse, this has to be the range of the inverse, and this has to be the domain of the inverse. The domains and ranges flip-flop. You follow me? Okay, that has to happen. It happened on this problem. It wasn't interesting because it was all real numbers for all the domains and ranges for all real numbers, but they did flip-flop. Here, they flip-flop, and that has to happen. Okay. All right, now we do the thing where you switch the x and the y's. So I put the y where it says g of x. Try to remind me that this is g of x if I accidentally write f of x, okay? Then I switch the x and the y. How do I get rid of that square root? Square both sides? Squaring both sides is an operation that you need to be aware is not something that you can just do and it's like a step like adding 2 to both sides. Adding 2 to both sides always keeps things equal. Squaring both sides, it keeps the equal things equal, but it makes things that are unequal into equal. So squaring both sides is a step that when you do it, you can't just do it and then just say, this is the same equation, because the inputs and outputs of this and the inputs and outputs of this are not the same. So we have to consider that when we do that. Okay, let me just explain what I mean. -5 is not equal to 5. If I square both sides, it makes them equal. Okay, so when you square both sides, you get extraneous solutions, and we're going to talk about that in just a second. Anyways, so then I want to get y alone, so I add 2 to both sides, and I get x squared plus 2. Okay, then I do my function notation. Try to remember it's g of x. If you accidentally wrote f with the little -1 of x, I probably wouldn't mark it wrong. That's just an accident. It's not really like a misunderstanding. This little -1, I don't know who came up with that idea for that to be the notation for inverse, but just so everybody knows, we're not raising anything to the power of -1. Okay, just like we're not doing g times x. G of x doesn't mean do g times x. This little -1 is not a power of -1. Whoever came up with that notation, it's a terrible notation, but it's been used for years and no turning back now. Okay, so you can graph this on yours if you want, but there's a problem with this, so you might want to hold off. Do you see the issue with our answer?
Yeah.
Right? If I reflected that blue square root function over that line y equals x, would it really be that purple one? No, right? We only want this part of the purple one, correct? Okay. So in this situation, we need to adjust our answer. So we saw a problem where we didn't have to adjust anything. We just did the inverse operation, blah, blah, it worked out. We saw a problem where we had to adjust the problem so that we could do an inverse. This one, nothing wrong with the original function. There's something wrong with our answer. So this is why you have to understand this domain range flip-flopping thing. The domain has to be 0 to infinity. The range has to be 2 to infinity. That's what has to happen. Okay, I'll draw these arrows again. You probably should draw the arrows on yours. But those domain ranges need to flip-flop. Okay? All right. Now, the fact of the matter is that this one doesn't have a domain of 0 to infinity. The domain of that one is all real numbers. So we need to add a technicality here that we only want when x is greater than or equal to 0. So this is our full answer here. In this case, we have to adjust the answer. So this might seem, super complicated, but there's only 3 types of problems. There's ones where you don't have to adjust anything. There's ones where you have to restrict the domain, and it will say that in the problem. It won't say find the inverse of this function that's not one-to-one. It'll say, how would you restrict the domain to find an inverse? And you would explain how you're restricting the domain. And then there's this type where you get an answer and you would need to know that you have to adjust that answer. Drawing a picture is a good idea. Let's do another one. And I'll try not to go too fast on this, but this one works out really nicely. It's just, we have to do a bunch of steps to do it. We don't have time to sit here and graph and really dig into the domain ranges. So let's just see if people know. There's only one value that's not in the domain of this one. 5. Okay, so most people are pretty good at that. 5 makes it undefined. The range, we're just going to do it really fast. But I would say in general, if you were doing the range this one, I would graph it and look at it and analyze it. But if you remember a little bit about rational functions, you might know there's only one value the range can't be. Does anybody know? It's 3. It's the ratio of these leading coefficients. There's more to it than just saying y can't be 3. But if you have a rational function with a horizontal asymptote, the rational function might hit thing and might not. You have to graph it to be sure. But if it's a linear over a linear, a line over a line, first degree over first degree, you can just divide these numbers and that's the number you'll never get. Okay? So it's a ratio of leading coefficients. So again, y can't be that number. Just trust me on that. All right. So now I want you to rewrite these and then switch the x's and the y's. The issue with this, and I believe you are probably taught this last year, the issue here is that you have 2 different y's. You're supposed to get y alone, but there's 2 of them. And so that causes a problem. All right, so we're going to cross multiply this thing. And I know some of you know how to do this, but I need to go a little faster so I don't run out of time. So I'm going to cross multiply this thing, and I get this. Imagine this over 1, if that helps you. And then I'm going to distribute the x, and I get this. Now, I still have 2 y's. I got to get y alone. All right, I'll ask if anybody knows what to do from here. All right, Desmond, go ahead. What are you going to do?
You got to get both the y's on the same side.
Get both y's on the same side. So I'm going to subtract 3y. This is 5. Yeah, I made a mistake there. That's 5x. Do you want me to leave that 5x or move it to the other side? Desmond?
I left it. I actually added both 3y and 7 at first, but then I realized that was problematic. I had a very roundabout way of doing it.
All right. Well, we're going to move. I'll just keep going. We're going to move this stuff without a y to the other side. So all of the things that have a y go to one side. All the things that don't have a y go to the other side. Desmond, you don't do very many call somebody else.
You can then have it be y times x minus 3.
So you're factoring out a y?
Yeah.
Okay, that's how you get it to be a single y. So you would get everything with y on one side, get everything without a y on the other side. If everything on the left side has a y, you can do a GCF and take out a y. And then we're going to divide by x minus 3. So that's how you get y alone. So this one has a lot of steps. What I'll tell you here is that this one has a lot of steps, but problems like this one, it's always these same steps, okay? This is a first degree over a first degree polynomial. I wouldn't give you a second degree over a first degree or a first degree over a second degree or anything more complicated than first degree over first degree. This is how these always are. And you do always do those steps. Okay. Now we're going to write function notation. It's h of x, inverse of h of x. I'm going to write this. Okay. Oh, we never said if this was 1-to-1, did we? So, I know we didn't graph this one. If you graph it, it's 1-to-1, okay? It looks it looks something like, boy, I'm kind of guessing here. It looks something like this, I believe. It's either like that or like this. It doesn't really matter. It's one of these two kind of graphs, and it's either like this or like this, and it's 1 to 1. Okay, so the original one is 1 to 1. Not all rational functions are 1 to 1. Not all rational functions, you could just divide those front numbers to get the range. But for these types specifically, a first degree over a first degree, they're always 1 to 1. And let's do the domain range of this answer. Okay, what's the only number that you can't plug into this answer? 3. Now look, did the range become the domain? Just like magic, it happened. All right. What's the only value that you think you can't get out of this? 5. It's dividing these front numbers. This type of problem, specifically this type of problem, it just always works out. So I don't have to restrict the domain. I don't have to adjust the domain of the answer. It just worked. So this is the inverse of that function. And the domain and range flip-flopped automatically. And so in some ways, this one is easier than the previous two. Step-wise, we have to do more steps. But domain range-wise, it's easier, yes?
Well, if you know that you have to flip the domain and range, couldn't you just keep the same equation and just flip the other two so that it would be, so you just flip the 5 and 3?
I don't know. I don't know if it would work out like that for every single problem. So I know what you're saying. That might work for a line over a line like this, but I don't guarantee it. And then I don't know about like if it's a number like 4 over x plus 2. Like that one, it would be 0. So I don't know. I'd have to check that. So I'm not sure. Maybe that's true. I don't know. I would just do these steps to be sure, okay? But I know what you're saying. You're saying, could you just switch these numbers around? And the answer to that might be yes. I don't know. But I wouldn't do it, okay? Just do it this way. And then if the domain ranges don't flip-flop, then there's an issue. But you're right, there might be a shortcut. There might be a shortcut to that. But I don't know about 0 degree over first degree. If it's first degree over 0 degree, that's just a line. We already talked about that. This is first degree polynomial or first degree polynomial. I showed you that, and I'll think about what you asked and see maybe there is some kind of rule that we can talk about. All right, so we're not done yet. Okay, if you fell asleep, wake back up, because this target is probably the easiest target to do if you know what they're asking you to do. And a lot of people do this wrong. And the thing that they do makes a lot of sense of why they would do it. Okay, it says confirm that f of x or f and g are inverses. So you have f of x and g of x are inverses. Now I would never give you a problem where they're not inverses. I'm not going to trick anybody. Okay, I also never give you ones that have complicated domains and ranges. Okay, these are both 1 to 1. These are both inverses, and you're confirming that they're inverses. Okay, so let's first talk about what you don't do. I don't want you to do the thing where you switch the x and the y. Don't write this down. This is wrong. So the thing where you switch the x and the y? Okay, that does not prove an inverse. That's the method for finding an inverse. It doesn't prove an inverse. Okay, so don't do the thing where you switch x and the y. That's a good idea, and it makes a lot of sense. But that's not a proof of it. That is the method for finding it. And the method for finding it, we already showed, doesn't always automatically just give you the right answer anyways. So how do you prove it? Okay, you go back to the very definition, which is this stuff. So going back to the definition, this has to be true. So what you're going to do, I use different letters here to make it easier. You're going to do f of g of x and prove that that's equal to x. And then you're going to do g of f of x and prove that that's equal to x. You got to do both of these, okay? So it is sometimes hard for people to remember what to do, But the people who can remember what to do, this is not hard to do. This is actually really easy to do. So I have to plug g of x into f of x, and plug f of x into g of x. And I'm telling you what they're going to be equal to. They're going to be equal to x. Okay, so I write this down. I write f of g of x. You got to write all this up each time. Then I'm actually going to plug g of x into f of x. It's not going to look pretty. I'm almost done here. I'm going to plug g of x, or f of x, into g of x. And again, this is not going to look pretty. Minus 2 plus 2 all over 3. Okay. So, now, this is what's going to happen. These are going to equal x. So, if you're on a test and you're doing this and they're not equaling x, just make them equal to x. Okay, they equal x. I promise you. Okay? So, this is what happens in this one. Okay? Try to show the steps. These cubes canceled. The cube root and the cube cancel, and you end up with this. And then these 3's cancel, and you end up with x plus 2 minus 2, which equals x. It's going to equal x. Having a problem over there?
Yeah.
Okay. On this one, the minus 2 and the plus 2 go away. The 3's cancel. You get cube root of x cubed, which equals x. They're going to be x. Okay? So if you can't, if it's not working for you, just fake it and write equals x. They're going to equal x. I promise you. Okay? So that's what you show. You got to show both of them. It's got to be like that. We don't have time to do number 6, but if you do that on number 6, they both equal x. Those are both inverses of each other, and we'll talk more about that as we review.